So that's done. So there might be some noise, and I'm really sorry. Some construction work is going on in the next building. I hope I'm like audible and my voice is clear. If it gets disrupted, please let me know. Okay. So this is the fourth class, and we have covered quite a lot of material. We have also done some codes. So let's just skip to in the last class. We were uh, dealing with lossless transmission lines, and I've left this as an assignment after we have covered this module. So this will be an assignment for you guys. Today we'll uh, co- uh, try to calculate the S parameters from the code that we did in the last class. Before we start with that, I'll like ask if there is any doubt from the code that we discussed in the previous class. Any questions on that? And did you guys find time to run the code, play with it? I had also left some questions. Any questions from the code, or if did you try to run these things and find any problem?
Thanks. On my side, I did run the code, but everything ran well. The issue, I had a very old MATLAB version, so I needed to change some things. It couldn't generate the videos. I've got a 2017 version, but eventually it ran. And then I had an issue where the pulse, remember you gave three pulses. There was a sine wave, there was a Gaussian pulse, and then there was a sine wave modulated in Gaussian. The code for the sine wave modulated in Gaussian, no matter what I did not produce a sine wave modulated in Gaussian. It just produced a Gaussian.
Okay, so for the last question, which I could follow was like uh, in the Gaussian, like sine modulated Gaussian pulse, you could only see a Gaussian pulse and no sine modulation, right?
Yes.
Uh, so for that, one reason could be that the sine waves frequency was much smaller than the Gaussian envelope. So if you increase the frequency, you might start seeing some sinusoidal pulse inside the Gaussian envelope. Maybe you can try changing the frequencies. I'd also see if there is issue with that. I could not follow the previous questions due to the noise. Can you please repeat the other questions?
No, it was just that, please.
Just that, right? And regarding the video thing, so that's totally separate from the FDTD part, right? So could you see the plot, running plot inside and see the wave traveling, right? You could see that.
Yes, yes, yes.
Okay, so regarding the video generation thing, like it's not necessary. I just kept that in the code so that if you ever want to save video files, you can also find like if you just search for it on the MathWorks website, you'll get the code. So I just copy pasted from the MathWorks question and answer like place. So you can try googling that and you'll get that. And regarding the pulses, I'll also see if there's some issue with that. But I think the issue could be that the frequency of the like sine wave was same as the Gaussian pulse and envelope, so you could not see any like crest and trough inside the thing. So I'll also check, but maybe try changing the frequency inside the Gaussian envelope for the sinusoidal case. Anything else?
I'll do so.
So one of the interesting assignment questions was to try cascaded transmission lines. So did anybody try this? And if so, did you find any trouble or were you able to do it? If not, that's all right. You'll have plenty of time after this course. So this is the fourth class. We'll do one more. And so I'll share the code for the S parameters after this class. We'll discuss lumped elements in the next one, and then you'll have all the codes that you need to like solve most of the simple problems for FDTD, and try reading literature on FDTD from research papers. So, and then you can try your own stuff. Okay, then. So there are no questions, no further questions from the codes that we did in the last class. Well, there has been one topic that I've been skipping till now, which was the stability of the FDTD method, and which was the Quran factor. So let's quickly discuss that. So the thing is, when we are trying to solve the FDTD problem, we have uh, unit cells, like we have the unit cells, and we are trying to solve FDTD code at each node. Okay, so for example, if you're trying to this is the time and space axis and stuff. So when we're trying to solve, what we do is when we first operate at first one node, and then we move to the next node. And this node, then these nodes are separated as delta s. Okay, just write delta x over here by delta x distance, and the time in which we move from one node to the other is delta t, which is our time step. Now we have to make sure that we are not simulating our code, like we do not reach the node before like faster than the speed of light. So we have to make sure that the time taken between the traveling from one node to the other follows this expression. Okay, so this expression over here are missing the delta terms. It is delta t equals to delta x by c naught. So we have to make sure that we do not violate this, or it is better if this is delta t less than delta x by c naught. So you have to make sure we do this, and this is for the case of one-dimensional code. But if it was a two-dimensional code, then the distance we have to travel from first node to the next node could also be in this direction. We're also traveling diagonally. The waves, since it is a 2D case and wave could travel in all directions, the maximum distance that you have to travel would be diagonally. And so this would, and for so if your velocity was c in this case, the velocity over here in this direction should be 2c, so that you reach the node in this at the same time. So in this case, this will modify to delta t equals to delta x by root 2 c naught. And similarly, if it was a three-dimensional case, if you consider a cube, the maximum distance that you'll be traveling would be from this node to this node diagonally, so diagonal of the cube, which will then increase to the delta 2, the root 2 would change from root 2 to root 3. So this would be delta t equals to delta x divided by root 3 c naught. And this goes on, so you can see a trend. There was root 1, this was root 2, this was root 3. So for an n-dimensional simulation, this would be delta t equals to delta x divided by root n c naught. So this is what the Quran stability criteria tells us. And you have to just make sure that you follow this, and everything will be all right. If you violate this, you might encounter some errors after some time if you start running your code. So this was pretty simple thing. You just have to make sure that you do not violate the Quran stability criteria. And how do you get the condition is based on this formula over here for the nth dimension, 1D, 2D, 3D. I don't suppose anybody who will go above 3D. So just make sure you do this. So any questions on this?
So you were saying that it's only applicable for 1D. Do we also use the same method for 2D and 3D?
Yeah. I okay. Well, can you repeat your question? Maybe I could not follow it. Can you rephrase it?
So the requirement t equals to x over square root 2c0, is it only applicable to 1D, not 2D and 3D?
So this condition is right. So delta t less than delta x by root over n c naught. So this is for the nth dimension. So if you're doing if your code works in 1D, you can put n equals to 1 and you get your condition. If you are simulating a 2D code, then you put n equals to 2 and you get your condition. And the code which for if you have written something for 2D, which this will also work for 1D, but it won't work for 3D. And similarly, if you just put 3 over here, then it will work for 1D, 2D, 3D. But if you don't, if this is less than 3, the code will break for the 3D case. So if you can also just put this as like instead of n, just put like 10 root c naught. Uh, so this will work for all the dimensions. But what will happen is that you have chosen a very small delta t now. So your code will take much longer to simulate 1 millisecond. For example, if you try to simulate 1 millisecond, we'll be doing a lot more time steps. So we try to optimize. For example, if you're just trying to solve for 1D, just put n equals to 1 and you'll get the sufficient criteria. Were you able to follow that, or do you have further? Like, can you rephrase question if I did not answer it correctly?
Yes, yes. Thank you.
Okay. Any question? Anybody else? Okay, so we have uh, covered all the topics that was needed to simulate the previous code. Now we'll work on the calculation of S parameters. So this is the paper which we'll discuss later. First, we'll read a little about the different parameters, the uh, admittance matrix, the impedance matrix, and the scattering matrix. We'll first look at that and then see a generalized form of the S parameters, which we get from power waves, which is the concept used in this particular paper. So for microwave network analysis, for example, if you have an N-port microwave network, this could be general idea or general diagram for an N-port network. So what we do is we take a reference plane where we'll denote the forward and back reflected wave, forward traveling given by Vn plus, and the reflected waves given by Vn minus, and In plus and In minus. These are the forward traveling voltage and current values. And we do this for all the ports. And so the total voltage at each port is given as a sum of the forward traveling voltage of the wave and the reflected wave, and similarly for the current as well. Now, if for the impedance matrix, it is given as the this by this relationship. So this is what if you arrange the voltages in the LHS in one column and the currents in the RHS, and if you put this matrix over here, this gives you the impedance matrix. This matrix is known as the impedance matrix, where where each entry can be calculated in this fashion. So Zij, for example, if this is 1 1, this will be Vi1 and V1 by I1, and if we have to make sure that the uh, the current at all the other ports is 0, and this should not be equal to k equal to j. So I won't emphasize a lot on this. I'm just covering it so that we know the different matrices on the relationship that we have between the reflected between the voltage and currents. Similarly, we have the admittance matrix, which is the inverse of the impedance matrix. And again, these have n cross. These are n in cross n in size, and you will have two n square independent quantities, but they could be reduced in case of reciprocal or lossless. So you can do further reading from Podzar. from where I have taken this material. And then we have the scattering matrix, which were developed because whenever you do measurements on your device, you can measure power at the ports and not the voltage and currents, which is difficult to measure. So you can measure power, and then so the scattering matrix or the S parameters are basically can be directly obtained using the devices like your VNA. So this is PNA, which is just an advanced uh, VNA. Yeah. So just the scattering matrix are basically have the entries as the S parameters, which we know, the S11, S21, S12, S224, a two-port network. So now we saw in this slide that the V plus and V minus and I plus and I minus are the quantities at each reference plane, and if you arrange them in again in this matrix form where you have the reflected voltages can be calculated from the scattering matrix and the incident voltages, or you can just write them in short like this, where each entry can be calculated from this expression. So the S parameters are, I think, is kind of prerequisite for this course, because if we go deep into these matrices, it will take a lot of classes. Uh, so do further reading on this, but I guess everybody knows about the S parameters, and our focus is to how do we calculate these S parameters from FDTD. Now, one thing, so there are some limitations for the traditional way of calculating the S parameters. So we'll first discuss the power waves. So these are again, if you want to do further reading, go through codes are. So the total voltages and the current can are given by this expression, where if this is the incident voltage and this is the reflected voltage, and similarly the current can be given if this is the characteristic impedance is forward and this is reflected voltages. Now we can find out the incident and reflected voltages from these expressions here if you just rearrange them, and the average power can be given by this expression. Now one thing you notice is these are imaginary. So, and if you're taking the real function on the of this expression, so these go away. What we end up is this the final result, where you can see that the total power lost is equals to the incident power minus the reflected power. Now, this result is physically satisfying because it expresses the net power delivered to a load is the difference between the incident and reflected powers. But this result is only valid if your Z naught, if this Z naught is real. If it is complex, this particular expression won't evaluate the same way, because this V naught term and the V naught minus term, they have Z naught inside them, and these won't be like the real values. So they won't this the particular term won't go to zero. So what we do is we and okay, before that there is another problem, is in this particular the solution for the PL. Okay. Uh, this can be evaluated. These expressions are only true for transmission lines. So if there is no transmission line, that is, we do not have a Z naught, then this particular expression fails. So, for example, if there is a circuit like this where we do not have any transmission line, we just have a generator. It's internalized impedance of the generator and a load. There is no transmission line, so we do not have a Z naught. And how do we calculate the power and the S matrix for this? So in this case, we define a new set of waves called power waves, which are kind of fictitious, but we use the variables a and b to denote them. So this is here is the expression for the power wave amplitudes A and B. So we write A as V plus ZRI divided by 2 root over RR, where the ZR and RR are ZR is the reference impedance, which we generally take as ZR as 50 ohms, because we characterize most of our devices as 50 ohms. And the interesting thing is the S matrix you can, this expression is valid for any ZR, and you can use this formula to find out the S parameter of your device for any reference impedance. Now, once we have the expression for the power wave amplitudes A and B, we can use this in the FDTD code. One thing you can note that in the previous slide we had the for the reflected and the transmit, the incident and reflected voltage wave expression like this, and they look very similar. They are the same form. It's just that over here we have defined this new term, and we call them as power waves. So they are very similar, so we can perform a similar treatment. So over here, this is your A and B, and using the A and B, you can again rewrite to write down your voltage and current expressions, and then find out the power delivered to the load. Now, now that we have this expression over here, and again these terms are purely imaginary, and if you are taking a real function, they go away, and we can see that the this term is also, this also says that the incident minus the reflected power is the amount of power available at the load. So we are getting the same conclusion, but over here we do not have the same restriction, because we have now included the impedance values, and it could be real or imaginary. So this result is more conclusive than the previous result that we got. And we have also removed the dependence of having a transmission line with uh, transmission line, so we can calculate this against any reference impedance. And we can also calculate the reflection coefficient from A and B, which is this expression. And if you try to evaluate them, we get the similar form that we already know. And if you put your reference impedance equals to the conjugate of the load, this will make the reflected power wave amplitude go to zero. So you won't see any reflection. So you can see the numerator over here. The reflection coefficient becomes zero at this, but when ZL becomes equals to conjugate of the reference impedance. So this is some useful thing to know to avoid reflections. So yeah, before we start with the paper, any questions on this? Okay then. So these texts is taken from the paper that we saw by R.J. Lubers. Do check out the paper. I've also included the paper in the folder which I shared, which had the books. So I've included the paper there. I'll also share the paper in the WhatsApp group. This image is taken from the paper itself, which shows a two-port network, and we have the forward traveling current as I1, uh, the current at port 2 as I2. Remember to check notice this direction of the current. We have V1 and V2 as the voltages at the port. We have VS1 as source at port 1, R01 as the impedance of the source at port 1. Similarly, we have R02 and VS2. Now, the reference resistances R0 and R02 correspond to the characteristic resistance for which the S parameters are determined. So these are the reference resistance to which the S parameter is to be defined. So for example, if you are solving our code, and we'll just take it as 50 ohms, because most devices are characterized around 50 ohms. But if you want to get S parameters for your device at different impedance value, and that too at different impedance value at each port, you're free to change the R0 I values for each port. So now we saw the power wave amplitudes, and we can write the terms A and B uh, as over here. Now the next step is to calculate the S parameters. Now the S parameters can be quickly written in this form. So the S11 would be B1 upon A1 when A2 is 0. So that means A2 is 0, and A2 is 0 means we do VS2 is supposed to be 0. Okay. Similarly, when we want to calculate S12, it would be B1 by A2, and your A1 should be equals to 0. A1 equals to 0 means uh, when this particular term becomes to 0, so V1 plus R0 I1 should become 0. And if we make the source at the port 1 equals to 0, then that problem gets solved. So we won't have this particular term. So that's how you do. So essentially, what I'm trying to say is, if you have a two-port network and you want to find out the S parameters, what we do is we terminate one of the ports as, for example, 50 ohms, and just put excitation on one of these ports. So we have a 50 ohm resistor at this port. We have a source at the first node at port one, and at port 2 we just have 50 ohm load. We put an excitation and calculate the A1, B1, A2, B2, and we see that if you are putting excitation at port 1, your A2 will be 0. A2 will be equals to 0, and we'll have A1, B1, and B2. So we can take B1 by A1, and so that will give us S11, and we'll have B2 by A1. This will give you S21. So if you put excitation at port 1 and just terminate with the load at port 2, you will get S11 and S21. And then in the other case, what you do is put excitation uh, put excitation at port 2 and some resistance of 50 ohm impedance for the excitation, and then your excitation at this port 2, terminate port 1 with 50 ohm. You will calculate A1, A2, B1, and B2. You see that, and this time A1 becomes 0, and so you and just we can take the ratios B2 by A2 and B2 by A1, which gives you S22 and S21. Sorry, B B2 by A2 and B1 by A2, which gives you S12 and S22. So just remember, you have to change the excitation for each case. In one case, excitation will be on the port 1, in the other case, excitation will be on port 2. And then just simulate your code, save your values, and we'll perform some FFT and get the results. We'll discuss the codes next, but any questions that you have over here? Yeah, sorry about the noise. I'm not sure how loud that is, but it's pretty loud here. Okay, then. So we'll discuss the codes and maybe things will become more clear. So these are the results that you'll get from the code which I'll share, where we have the S11 and S21, and S22 and S12 will be left as an assignment. If you face any trouble, we'll discuss in the next class. And so this is the phase plot, and this is the magnitude plot. And since our code simulated just a simple transmission line of length 2 lambda at 2 point, okay, lambda by 2 maybe, lambda by 2 at 2.45 gigahertz. So this was just a transmission line of 50 ohms, terminated in 50 ohms. We have an excitation at port 1. So this and since all the there are no elements on this, we have S11 much below, which is So this means that all the power transferred from the generator to the load because everything was matched, and as the S21 is 0 dB. This means all power was transferred, and almost negligible power was reflected. So what we did was we put the reference impedance at both the ports as 50 ohm. The the impedance of the transmission line was also 50 ohm, and the excitation was a sink source. So I hope everybody remembers the Fourier transform thing. If you have a sink function in time domain, its Fourier transform becomes a rectangular pulse in the frequency domain. So I hope everybody remembers this. And based on the this based on the first node thing, the sharpness of this, uh, if this is something 1 by TS, this will be FS. Some sort of relationship is there. So you can choose the value of that the width of the thing function in time domain, which will give you the length of the response in the rectangular response in the frequency domain. So the idea is if you what this particular rectangular pulse means is that if you're giving a particular power in at each frequency, right? So if I choose this to be as 10 gigahertz, for example, so for up to 10 gigahertz, this is a rectangular pulse, means each frequency, for 1 gigahertz, 2 gigahertz, at each frequency is getting a power of, for example, 0 dBm. If I'm sending a power, and if you take see the response of the system uh, at so this is given at port 1, and at port 2 what will happen is you might get some sort of response. And if you take the ratio of the power at each frequency at port 1 and port 2, you will get the ratio of the power, which is essentially the S parameters. So what we do is we send a flat response at port 1 and see the response at the port 2, and since this is a flat response, whatever response that you get at port 2 will essentially be the S parameters. And to get a flat response at flat excitation in frequency domain, we use a sync function in time domain. Uh, was this clear, or maybe should I try to like explain this in another form? Like anybody has any questions on what we are trying to do, like how we are trying to extract these parameters in time domain? So I'll let me know
Uh,
if you have any
ju-
questions. Yes,
just a question.
yes,
I see, I remember that the S parameters include both magnitude and a phase, right? Uh, and then sometimes there's the other element, things like group delay. Are all those things extractable using these equations? I'm just trying to figure out how. I remember that you said if we provide a Gaussian pulse, the FTD method enables us to span the entire frequency band, so we don't need to do a frequency sweep.
yes.
But then in terms of getting group delay, getting S11, the whole 4 parameter matrix, yeah, I know you are getting the. Are you saying that with these equations we are able to extract that, and that is what you are showing us today?
Yes. So um, the the first thing that you emphasized was, if I forgot to emphasize that we don't have to do a frequency sweep, so we just send in one pulse and we can get the entire S parameters. Regarding the group delay and all the things which it has to be, you can do it in the post processing. So once you have sent an entire band of frequencies together to your device. For example, either using a Gaussian pulse or by using a sync function, which is a rectangular pulse in the frequency domain. So you're sending power at each frequency in the frequency domain altogether, and then you get the response in the frequency domain. And once you have, so you'll get the uh, so you have the information of what signal you sent in for at each frequency, and then you can calculate whatever parameters that you need after that. So you what we are trying to do is that we have a rectangular pulse in frequency domain. We know its time domain equivalent from the inverse Fourier transform, and we send this. We get some signal out at the port two. That could be any signal. Then we perform FFT and get its frequency domain response. And so you will have the information of what you sent in the at the port one for each frequency, and what information you got at each frequency at port two, and then you can use all your formulas. For example, for the S parameters, we are using the power waves concept. I've never calculated group delay, but I think it should be fairly easy if your the S parameters is usually the most tough thing that you have to figure out for a time domain thing. For the group delay, see if there are papers. There must be some papers out there. You can go through them, but yeah, it's fairly easy. Up till now, I had given you Gaussian pulse, a sine function, and a sine modulated Gaussian. Now we're seeing a fourth kind of excitation, which is sync. So I had to make sure that everybody follows that what a sync function is and how it looks in the frequency domain. I hope I was able to answer a question and you were able to follow what I was trying to say. And do you have any follow-up questions on this?
Thank you.
Okay. So we'll just look at the codes now. So essentially, the only change from the previous code is that instead of using a Gaussian or a sine, we are using a sync function. You can also do calculations using a Gaussian pulse, but I won't recommend because it has a rolling off fashion. Instead, sync has a more sharper cutoff so whatever your frequency band you are on to calculate your broadband as parameters, you can just put your cutoff frequency there. Okay, so this is the code, and all of this is same. We have whichever already discussed. So the only change is over here at line number 23. We have included the sync functions roll off. So if the sync function looks like this, so this is your TS, and which is this TS, and which will give you which is being calculated using FS. So this TS corresponds to the this is this for rectangular pulses for response at FS. So for example, this is 0 over here and this is 10 gigahertz. So if your FS is equals to 10 gigahertz, your TS will be equals to 1 by FS. So this we are making sure that we send same power for all the frequencies up to 10 gigahertz. You can also modify this, and the other value which the sync function will use is that initial delay in sending the signal, which is T naught. The rest of the code is same. So again, this is all same, I believe. Yeah, so this is all same. I have just increased the total time step over here to make sure if there are any to and fro reflections in this in the simulation space. Now the yeah, over here I have just pre-allocated some variables. The and we're calculating the length of the FFT. So I've used this expression over here. So we have the total time steps, and then the FFT has to be calculated. Its length is usually of this form 2 power n. So re do some reading on FFT, but It has to be in the order of 2 power n, and to make sure that it is of this length, I'm using this function over here, which finds out the next power of 2 from t steps. So once we have calculated the FFT length, we are creating another variable frequency, that which uh, is initialized with zeros, and now this frequency that will be filled with the values of the frequency dot. So to plot in the your frequency axis, I'll need the value of each frequency points, right? So this is just calculating at which frequency points we'll get the FFT data. So you have your FFT function in MATLAB, which if you put some function, if you put some way value inside the FFT, it will give out the FFT. And now once we have got this FFT of this particular function, we want to plot it. So this FFT will give you just the y-axis, and over here is we calculate the x-axis. So we are just filling in frequency that with uh, this df is your delta f for the this frequency axis, and we are just initializing each frequency point. So this is some pre-calculation needed for FFT. We have just allocated the S parameter value, since this is the source is only at port 1. We'll need S11 and S21. For S12 and S22, you will have to do a next simulation. Any questions over here? Okay, so we are doing some pre-calculation before FFT. So this is, we have calculated the x-axis, we have pre-allocated the values, and now so this is all okay. So over here, this is the new excitation, the sync function, which looks like something like this, and its frequency domain response is something like this. This is all same for your FDTD code that we have done. Okay. Now the next thing that we do is we save the values. So what we are doing is we need the voltage value at each port, voltage and current values at each port. So we save that over here. So Vs is the voltage at source, VL is the voltage at load, Is is the current at source, and IL is the current at load. And what we are doing is, for each iteration, you will have some voltage value at the first pole. So you have your simulation space, right? And this starts from 1 and goes to your ZDIM. This is for the voltages, and for current it starts from 1 and it goes to ZDIM minus 1, because we are calculating uh, voltages and currents at different points, right? When they're next to each other. So for current, ZDIM would be outside the simulation space. So we take the point before the load. So and what we do is we save the voltage and current value at both the edge boundaries. So V1 and VZ1 and IZ1, we are storing them in one array, and VZ ZDIM and IZ ZDIM minus 1 in IL and VL. So we're storing the voltages value at the boundary. Any questions on this? Okay. So we did some pre-calculation for FFT. Then we generated the values for the x-axis. We have now stored the time domain value for V source, current source, voltage at the load, and current at the load. Now we have time domain data. Now, next we need to do is perform FFT on them. So this is the part where we perform the FFT. Read more about the FFT thing in MATLAB. So we are just directly using a function. If you are not satisfied with the performance of FFT function from MATLAB, you can write your own FFT code, but I won't help you with this. So we are using the FFT function from the MATLAB, and the FFT function from MATLAB requires two inputs. One is the uh, data on which you want to perform the FFT. For example, we are using the voltage at source over here, and the next is the length of the data. If you do not provide this, MATLAB will automatically use this value and use the length of the length of the data which you have given and pad zeros and make it of the some form of 2 power n. But we are explicitly giving the length of the FFT, and then you divide it with the FFT length value to normalize it. So this is how you perform FFT on the data. And we do this for voltage at source, voltage at load, current at source, and current at load. So this is how you perform FFT. So we initialized the variables, then we did some prerequisites for FFT. Filled the values for x-axis. Now we save the time domain data. We performed FFT on the time domain data. Now next we need to calculate are the power wave amplitudes. So we had seen the formula for A and B. It was something of this form: V minus R I, V plus R I by root over 2 Z naught or something, right? So, and similarly B was V minus Ri divided by root over Z naught. So we are using the same formula over here. Uh, you will see there's this thing over here where I've changed the sign of over here, because over here B2 had V minus Ri2 by root over 2R not. Yeah, and in that case, why I have changed this minus to plus is because I had said you have to notice that in the expression the currents the I2 direction was towards the generator, and what the direct in the general direction which we are taking positive is this direction. So I1's direction was all right, but I2's direction was the opposite. So we just change the formula. We just change the symbol over here. So we have calculated A1, B1, B2, and your A2 will be equal to 0 because we do not have any source at port 2. So once you have got A1, B1, and B2, what we are doing is we just take their ratio. We just take the ratio, and since each of them A1, B1, and B2 are vectors, we do a vector division over here. So this B1 B underscore 1 divided by A underscore 1, and sorry, so this B underscore 1 divided by dot slash A1 implies that B underscore 1 and this. Okay, so MATLAB has starts from one index rate. Becomes this is 1. So it does like each entry is divided and not the entire matrix. So similarly, this will imply that the next value for B1 at index 2 is divided by uh, A1 of index 2. I hope you follow this. So this make sure that you put this dot symbol over here for the vector multiplication or division in uh, for calculating the S parameters. So once we have done this, we get the S parameters, and since these are complex values, you can just plot them. Use absolute to plot the magnitude, and use angle to plot the phase. So if you use angle, you will get it between minus pi to pi. And what you can do is multiply, scale it to get it would be between 180 to minus 180 to 80 degrees. So that was it. That's how you calculate the S parameters. Any questions on this? Sorry about the noise. It must be really loud. But if you can hear me, do you have any questions on this? Okay, so any questions on this?
Yeah, I'm interested, Prof, on the the other parameters like the S22, S12, because I've seen that you've skipped them probably deliberately. Yeah.
Yes. So um, they are left as an assignment. The okay. So any question apart from S22 and S12? Any questions from in the calculation of S11 and S21?
Just a question, Prof. If you go back to 2 pages back, where we save the values, yeah, just one forward, where we save the IV, the currents in the source and the voltage in the source. Yes, there. So this is on every iteration. So what you mean is that both the current and the voltages, are they in time domain there? Do they span all the frequencies? Uh, 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 I just wanted to know that because for one to be able to extract the S parameters, we have to sweep across all the frequencies. So what you mean is that they are basically a vector in all the frequencies of concern.
Yes. So over here we are saving them in time. So when we said we are providing a sync function, it means this time domain signal has all the frequencies.
Yes.
So and what we do is we say, for example, if this is your simulation space and we have a source over here, and the sync function travels from port 1 and goes to and slowly to the port 2, and it some of it will be reflected, some of it will be transferred to the load. So we save the voltage value from T0. For example, this simulation started at T0 to whatever T steps simulation time. We save the voltage value at the load and at the source at all the time instants. So if you look at the time domain data at each at the source, you will see that after some instant there was a sync source which was generated at the source, and at the load you will see that after some instant there's some voltage signal had reached the load, and then after some instant you will see that if something was reflected from the load, it went back to the at port 1. You'll see some reflections, and again once something was reflected back from the port 1, it will again travel to the load port, and then again you will see some reflections. So this will go on, and we store all this voltage data and current data in time domain. And once you have all this data, we perform an FFT. And since the signal had all the volt uh, frequencies, if you take a FFT on it, you will get a square response, and maybe some reflected thing will be added to it. Some reflection was there. So you will get a frequency domain response at all the frequencies. And since you know that you sent a rectangular plot in frequency domain, and you get some value of voltage and current at the both ports, you can just use these values to calculate the S parameters, which are essentially at each frequency what was the power that you sent, a power incident reflect, yeah, so S11 S21, for example, the power which was received at that particular frequency at port 2 divided with the power which was sent at port 1 for that particular frequency. And since the time domain data has this value, we use the time domain data to perform FFT and get the power at each frequency. Did that make sense?
Yes, yes, please. Thank.
Okay, so I'll share the codes, and what you can do is play with these things. What things which I used to do was also record the for example, if this was a simulation space, I would record the value at different points as well, and then perform FFT and see which signals reached till which point. And this an interesting analysis could be if you have made a filter in this case, for example, if there was some filter, what you can do is analyze which signals get filtered at which incidents by calculating the you just record the voltages at each point and perform an FFT and see which waves reach till which node. So these are things which I played when I started with FDTD. Maybe you guys can try that as well. Uh, so let's discuss the assignment 3 and your question as well. The assignment is to modify it is to calculate S12 and S22. Now, what you need to do is the code that you have has is of this form. You have V0, which voltage at the zeroth position, which has some code, and then you have some source value, which is given by pulse. And then you calculate from, sorry, not V0, V1. MATLAB starts from indexing from 1. Then you have from V2 to VZDIM minus 1, some things go on your code, and then your VZDIM is evaluated with some R0 or Z0 or some RL or ZL value. Now, what you need to do is modify this so that this gets terminated with some load R0, which could be 50 ohm. Modify the VZ statement so that it has a pulse, and then run the code. In what will happen in this case is that you will have excitation at port 2. Your excitation will travel to port 1, record the values at of V S like at the initial, for example, VI and I and at so in the, okay, maybe you can just write, since source is over here, VS over here and IS over here, and since now load is over here, so VL and IL over here. So at now in this case, your port 1 has VL and IL, and your port 2 has VS and IS. And then you can again calculate your A2, B2, and B1. Your A1 will be equal to 0. And once you have calculated these values, you will get your S12 as B1 by A2 and S22 as B2 by A2. So I'm leaving this as exercise because if you are able to do this from the code which I share it with you, you will be confident that you have understood the material. And then there is again a little higher level exam assignment as example. You have to design a low pass filter or a high pass filter of your choice, which is essentially cascade of different Z0, Z1, Z2 values. If you arrange them, you can design a filter. So if you have time, maybe you can do that and then calculate its S parameters.
So, Prof, will you be able to also share with us the solutions? Because what you are talking about really touches our everyday work. That's the reason why I came for this course. But really, the designs, how we do them at the moment, it's by drawing the physical structures and using a solver like HFSS and also XF to do this. But one is very interested to know it from first principles. If you would be kind enough to also share with us the solutions. Yeah.
Okay, so since I came up with these questions just last night, I'll try to maybe in some time, maybe over a week, share code for the calculation of S12 and 22. Regarding filters designs, what I have done those, but they are like they have been submitted to a conference. Maybe once they come online, I'll share those because I right now do
Ye-
not have time to create
Yeah.
examples and share them.
Yes. Yes.
Maybe in
Yes.
some time when they come online, I'll share it with you.
Please. 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 Yeah. Okay. Thank you.
Yeah, so I think this was all that we had planned to cover today. It was pretty small class because in the last class I took a lot of time. So that we have done the calculation of S parameters. Please let me know if you face any trouble with the material that we covered today. The next class will try to model resistors, inductors, capacitors on transmission line, the lump components, and I think we'll end our lectures here. um, we probably won't be able to model CRLH transmission lines, but like whatever we cover in the next class, this will lay the foundation of if you want to model CRLH transmission lines. So
Uh,
essentially, what we have done is we had an inductor and capacitor, right, for the model which we are trying to do, and a CRLH is essentially has a capacitor and an inductor like this again. So in the next class, I will show, for example, if you want to model a capacitor with a transmission line like this, or if you want to model a inductor like this. So this case and this case will cover in the next class, and then you can combine these to model the CRS transmission line. So we'll probably not be able to cover it in this class, but I'm sure there will be enough material for you to model this.
And then, Prof, last question. We only dealt with lossless transmission lines. What happens in the case of lossy transmission lines?
Okay, so the lossy transmission line, if you send a Gaussian pulse, its amplitude will diminish and there will be some reflections. So those things will be there. So again, for lossy transmission line also, we have resistors over here, right? So this is a lossless transmission line. And a lossy one would be you have a resistor over here, inductor, and then there's a capacitor, and there is a resistor again in parallel with it. So we will cover these cases as well. Resistor in series with the transmission line unit cell, and resistor in parallel with the transmission line unit cell. So these two cases we will cover, and again these two cases combined can give you the lossy transmission line.
Okay. Okay. Thanks.
So we'll do it in modules, and again, leave these things as example, like assignments for you. And if you are able to do this, I'm sure you have understood the material really well, and like you are a master of this thing. And maybe I'll join your course when you teach them in your classes. Okay, so that was all for today. Any questions? Else will end today's class. Okay, then if no questions, I'll just stop the recording now.
Thank you. Thank you, Prof.